Hi, I'm Varjan Gorgian. I'm a research astronomer at NASA's Jet Propulsion Laboratory. I've been challenged today to talk about one concept at 5 different levels of increasing complexity. Today we're going to be talking about black holes. A basic definition of a black hole is that it's a lot of mass crammed into a very tiny volume such that the escape velocity is the speed of light. So have you ever heard of something called a black hole?
What is a black hole?
Well, it has to do with a lot with gravity. Do you know what gravity is?
No, not at all.
It's what keeps us on the Earth.
What?
The reason we're not just flying off the Earth is because Earth has gravity. So if we throw something up, it comes back down. So that's why when we're walking on the Earth, we don't fly off the Earth, because the Earth has gravity and it keeps us down. Nice. The main thing about black hole to remember is that it's just, like I said, how the Earth holds you down, the black hole pulls you in as well. Now try and take the ball from me.
Why do you hold it so tight?
I'm holding it tight to show you that when you're trying to pull it, a black hole will really hold on to it with its gravity.
I got it.
Yeah. The main thing is that if something falls into a black hole, it can never get out.
What about the Earth? What if it rolls into it?
If the Earth rolls into it?
Yeah.
It would be bad. We wouldn't be able to get out.
So it can never happen?
It's not likely to happen, no.
Well, in movies, right?
Well, yeah, definitely in movies.
Yeah, but it's not real because it's just pictures of it.
Yeah, exactly.
What if I went in there?
The black hole will sort of stretch you out as you're falling in.
It'll like stretch my body out?
Yep.
What?
So what do you think about black holes?
It's kind of dangerous.
So tell me, what do you know about black holes?
Well, I know they're created when stars, once they start growing, it can't expand anymore, so they collapse inward.
You got a very good idea about it. Basically, you have a star. At the core, it's generating energy, which is countering the pressure of all that mass being pulled in by gravity. Once it can't generate that energy anymore, the core collapses. Once the core is collapsing, it keeps collapsing and collapsing and collapsing. And that's the critical thing that makes a black hole. You have enough mass in the volume such that the escape velocity becomes the speed of light. Once light can't escape, hence the black part. But that's the thing, is that just because there's an intense amount of gravity very close to a black hole, things don't start behaving differently. And my favorite analogy is a vacuum. Everybody thinks like if you point a vacuum cleaner at something, it's just gonna suck everything in.
But no, the wind, the pull isn't, if you're not close enough, it doesn't work.
Right, you will feel the gravitational pull and it'll redirect you in some way. And if you're far enough away, it's just like you're very far away from the sun or something else. If you're close enough, it will divert your path more. If you're close enough still, then you will get what are called tidal forces, where the difference between, for example, if you're standing next to a black hole, the difference in gravity between your feet and your head actually becomes significant. Next time you see a science fiction movie and somebody says, oh my God, we've been caught in the gravitation field of a black hole and we're gonna fall in. It's like, no, just if you're far enough away, just thrust a little bit this way and then you'll just slingshot around the black hole.
So are there any movies that actually do like get space right?
I wouldn't call it educational, but the movie Interstellar actually had as one of the people involved in both writing it and as a science advisor, Dr. Kip Thorne, who's a professor at Caltech, who was part of the team that detected gravitational waves and just won a Nobel Prize for it. So he made sure to try and get it as accurate as possible. So Interstellar, I think, is one of the best examples of getting black holes right.
So I'm assuming it's hard to like detect a black hole besides if things are close enough that are being pulled in. So it's basically theory.
There are multiple theories. There's observational evidence more than some other theories that are really feeding into this, because now we have the instrumentation, both in X-rays and infrared in particular, because we don't have a direct optical line of sight to the center of our galaxy because there's just a lot of dust in the way. But the infrared can penetrate the dust, the X-rays can penetrate the dust, the radio can penetrate all of that dust. So by combining all of these different wavelengths, people are really coming to a point of, okay, how is this happening? By looking at different wavelengths of light, we can get a better sense. But they're still working on the theory. It's not all done. So far, what do you know about black holes?
I never knew beforehand that how hard it was to get actual data of the black holes itself. First of all, they're dark and like they're so far away, it's almost impossible just to get a good image of them. They were discussing a project in which multiple radio telescopes of some sort, like are like pinpointed all across from Greenland to South America, and like and they're trying to get an image of the black hole in the center of our galaxy, because as opposed to just recording its impact on the surrounding stars and planets.
So we've had now effectively two different ways of getting more direct measurements. One is the LIGO, which is the Laser Interferometer Gravitational Wave Observatory, which is where we're getting the ripples in space-time coming off of the merging of black holes. The other one that you're mentioning is actually called the Event Horizon Telescope, where they're using radio waves to actually image the event horizon, that region where light cannot escape, from the black hole at the center of our galaxy, which I know they're working on right now. It's an amazing thing, but that'll be the most direct imaging of a black hole.
Yeah.
LIGO is a direct detection of the consequence of the merging of black holes. The critical part has been, for supermassive black hole at the center of our galaxy, we've seen the stars orbiting it, and we've measured the mass that way. So if you look at a spinning black hole, it actually fundamentally alters the emission that's coming off the stuff that's falling into it. These are discovered as what are called X-ray binaries. That is, there's an X-ray member of the binary that is emitting in the X-rays, and it's really not very bright in the optical, or if at all. So there's always, people are looking at these X-ray binaries.
What sort of technology and like, I guess, tools have you been using in your studies, or like just in general in the study of black holes? For
my studies, I actually, when I started at UCLA in graduate school, I worked with a professor named Matt Malkin, who was gotten a lot of data observations from the Hubble Space Telescope. So that was one of my very first projects to work on it. So any space-based observatories have been a really big advantage. And then I've moved on now to the Spitzer Space Telescope. In addition to that, then there's other people who've used a lot of X-ray telescopes, NuSTAR, Chandra, and I've used data from that. It's been a combination of both ground-based observatories as well as space-based ones, and going everywhere from X-ray observations, not done by me, but certainly ultraviolet, and then optical and infrared particularly. Those are the ones that I've been most involved with. What got you interested in studying black holes?
The way I got really interested in this field is I actually first came to Caltech as a summer student, and I started working in this research group called the NuSTAR group. Right now I'm doing my PhD in the field of active galactic nuclei, which are the most luminous compact objects in the universe, and it's because of the extreme accretion that we're seeing onto these supermassive black holes. We don't have such a simple picture that this central black hole is surrounded by this donut-shaped torus of material, and that all these different classes of AGN simply arise from a viewing angle effect of this torus is a very oversimplified geometry. And
which is, by the way, when I was just starting out in graduate school, that was the hot new thing. So that was just like, oh wow, this might be it. And then, but very early on, it was as I just started it was basically my second year of graduate school. It was like, this is not that simple.
It isn't.
Everybody's been just coming at it from different wavelengths at the optical, infrared, but definitely the X-rays has been one of those things where it's like, oh, finally.
And we've come a long way. By seeing a wider range of the spectrum, we can elucidate more about the circumnuclear geometry. And there's just been so much progress made with all these new spectral models that we use to fit AGN spectra. And the different types of classes of AGN, like type 1 and type 2, are believed to be just a viewing angle effect of seeing this torus at different angles.
It does seem to be that it may not even, in parts, it may not be even connected to this tiny little torus at all, because part of the work that I did and others have done is that Type 2s preferentially live in different kinds of galaxies than Type 1s, which should not in any way have to do with something such a small scale. They tend to be in smaller bulged SB and SC type spiral galaxies. So there's something also having to do with the environment that gets you to be a Type 2, and still maybe timing-wise, but there's something else that's going on a larger scale, because the type of the AGN should not really correspond to the host galaxy, but it seems to. And that was one of the things that we were finding out, and that was one of the early little ideas that individually, just as the torus model, the unified model, can't explain everything that we were observing at the time. But it is one of those things that they're super luminous, they're all over the place, and we don't have a really good picture of it, which makes it exciting to study.
Yeah, and I think, pushing towards the future, like this whole multi-messenger era and utilizing all the different wavelength telescopes that we can is really the way to go. We cannot just build up a picture purely from X-rays alone or purely from infrared. And I think there should be increased effort to try and have more coordinated observations with the different telescopes like NuSTAR.
Well, that makes sense, but it's always so difficult to get that.
It's difficult to even just coordinate, soft X-ray and hard X-ray telescopes together, like getting, time for both simultaneous, say Chandra observations and NuSTAR observations, or XMM and NuSTAR. It's a difficult thing, but I think we really need to get a clear picture to be looking at all wavelengths, of course.
So how do you do your observations in optical and infrared?
So fortunately, I'm also doing it from space with the Spitzer Space Telescope, so particularly in the infrared. And my main interest has been to try and study the environment around the supermassive black holes, not as close as where the X-rays are coming from, but clearly there's something from the X-ray corona that illuminates the rest of the accretion disk and the dust that's further out. And so fundamentally, that's one of the key things that I'm trying to use, is trying to see how long, once you've got this sort of pulse that's generated close to the black hole, propagates out. And so you can use optical wavelengths to see that the accretion disk lights up in the optical a little bit as it gets heated up from the X-ray. And then later on, the infrared dust, the dust absorbs it and emits it in the infrared. And so I love the ability to exchange time for resolution, because these structures are so far away that we're never going to get a telescope big enough or that has the resolution to see the accretion disk or the dust distribution around the supermassive.
So do you get dimensions of the disk out of that?
Yeah. Again, we don't know exactly where XYZ 0 is. We're assuming that it's the X-rays that are coming out are very close to the event horizon of the black hole. But this is still, your realm of X-rays to really figure out those kinds of things. But once the X-rays, once the photons hit the corona and are rescattered and up energized, and then they start illuminating the accretion disk, it heats it up. And so just by the light travel time, when the optical, if it gets, brighter and fainter, and then the infrared gets brighter and fainter 2 weeks later, then the dust is 2 light weeks away from that. So it's a one-dimensional one. So we're averaging, so we don't get the two-dimensional or even three-dimensional one. And then we've done it now. Of course, we have better telescopes. There was a project where you could do it with the Hubble Space Telescope in the ultraviolet. You could use the Swift Observatory, which had optical and ultraviolet. And then from ground-based, we did optical, and then from space, we did it with Spitzer in the infrared. So you could actually see this bright flash go off in a nearby AGN called NGC 5548, and then you see it propagate as it warms up the disk as all that light is falling onto it, and then eventually it hit the further away where the dust is, and the dust tends to radiate in the infrared. So we got basically a structure, and you see this flash bulb go off, and then it illuminates effectively the structure.
So you can map out the dust. Where do you see it?
So you do see it at basically the dust sublimation radius, and you see it and it tells you depending on what kind of dust it is. And it's actually one of the problems for me studying whenever we try and do X-ray studies of low luminosity extragalactic nuclei in nearby galaxies, because there are all these X-ray binaries that are also emitting X-rays, which make our lives difficult, but they're also black holes. But it's this really interesting sort of both. It's great, but it's also a source of noise for those of us who are trying to do X-ray observations of nearby galaxies.
We have the same problem. We can't see the actual black hole underneath all these very bright X-ray binaries.
It's a weird thing to be sitting in your own galaxy, but not be able to separate out this 4 million solar mass black hole accreting next to how massive is like 2 to 3 solar masses for the X-ray binaries? The
X-ray binaries, so they're typically like 10 solar masses. So from 3, that's the smallest one you can have is from 3 solar masses, and then all the way up. So that's where we have LIGO, and LIGO has now directly. This was all theory before that we knew that this was going to happen. Never seen it before. So LIGO is now the first time that we have been able to completely verify this theory that you can have black holes and neutron stars merging together. And so what happens in the case of 2 neutron stars, when they merge together, now suddenly they become heavier. They become heavy enough to turn into a black hole. And so the first of these events happened in August. And what happened here is you had these 2 neutron stars that spun around each other, and then they merged. And then for a very short time, we're talking about 100 milliseconds or 10 to 100 milliseconds, it actually remained a neutron star. Probably it was hypermassive neutron star because it was spinning so fast it didn't collapse on its own weight. But then, the angular momentum gets dissipated away from the object, and then at that point it can't maintain its own weight, and then it collapses and turns into a black hole. All this theory that we knew about is now finally being validated.
Which is great, although it still doesn't help us in the AGN community
No,
because we don't know how the millions to billions solar mass black holes came to be. But it's at least we're building up, or hopefully that at some point, and by understanding these lower mass, how these lower mass black holes came to be, then we can see whether a large scale number of mergers can potentially give us this, or you really need something, another corridor to fundamentally get us something that's a million solar masses, on the minimum side, but definitely, we've gotten those which are billions. So we know we can merge the million solar mass black holes to get the bigger ones. But how do you get to those in the beginning, particularly so early in the universe when you get quasars at really high redshift, so they're really early on?
Yeah, it is odd. It is very odd. I mean, the other thing that's a little odd now, we're going back to stellar mass black holes, is so we look at a lot of supernova remnants, and we see them. We can only really see them in our own galaxy, and so we have a lot of supernova remnants. And so how we see them is you see the expelled mass from the star as it dies, so that creates an extended source, and then you look for the compact object that was left behind. And what's interesting is that you quite often see the neutron stars because they pulse, so they're easy to see. But so far, we've not found a single black hole at the center of a supernova remnant. And so, which is interesting. And so you say, you should see them. You ought to see some fallback. You need some matter, you need something. But no, not yet been detected
But then this goes to the idea that you don't have a core mass, that a supernova with a black hole as its final result actually never has any kind of expulsion, that it all just goes.
Yeah, that might be, yeah.
Which was one idea. But again, I'll leave this to the theoreticians. I think there are problems with that as well.
Right.
I call it job security.
That's right.
we have a lot of things about black holes, both in terms of their formation or even how they exist as they are and how they're interacting with their environment, that we're still not understanding.